Okay, geometry, I am not feeling my best today, so I'm going to try to run through this video as quickly as I can. Feel free to watch it on a faster or slower speed or whatever you want so that you guys can keep up. 6.3 deals with the last two of the four special segments or lines that we're learning to draw in triangles in this chapter. And it starts with medians, which our definition right here says is a segment connecting a vertex of a triangle to the midpoint of its opposite side. So in any particular triangle that you may draw, what we're going to do to draw a median is locate the midpoint of one of our sides here. So if I were to just kind of guess right here and say that this looks like the midpoint of line segment AB, and I'll call this point C up here, we can tell that point M is a midpoint by putting some tick marks here for AM and MB, showing that they're congruent. And then the median of that triangle is the line segment that is going to go from vertex C to the midpoint of its opposite side, which would be M right there. So what we just drew in red is one of the medians in that particular triangle there. Once more, it goes from any vertex to the midpoint of its opposite side. So that's what a median looks like. And in a moment, we'll draw all of those in a triangle and see how they all interact. So, very first problem we have right here, the directions tell us that AZ is a median and we're supposed to solve for X. Well, the fact that AZ is a median tells us that point Z right here must be the midpoint of side BC, even though I don't think I drew this very accurately. So BZ has to be congruent then to ZC, and that's going to give us the information we need to set up our equation here, guys. That's 7x minus 11 is going to have to equal 5x plus 9, and we'll solve that nice and quickly. Subtracting the 5x gets us a 2x on the left. Adding the 11 to the right gets us 20, and we should end up with x equals 10. And just to double check that, 7 times 10 would be 70, minus 11 looks like it's going to be 59. And on the right, 5 times 10 is 50, plus 9, 59 there as well. So x equals 10 looks like our answer. Okay, that's a very simple median problem. Now, the interesting thing with medians happens when you start to draw all of them within a triangle. So we have a theorem here, 6.7, called the centroid theorem. And it says that the three medians of a triangle are going to intersect at a point called the centroid. That's a new word, kind of a cool sounding word. And that the centroid, here's where it gets interesting, is located 2/3 of the distance from each vertex to the midpoint of the opposite side. So in this diagram right here that we have drawn already, all three medians are drawn. That's going to tell us here that F is the midpoint of AB, so tick mark there. D is the midpoint of BC, so we'll do a double here and a double here. And E is the midpoint of AC, so a triple tick mark to show that AE is congruent to EC. That means that all three of the line segments, AD, CF, and BE, are all medians. Now you'll notice once again, just like what happened with perpendicular bisectors and angle bisectors in the last two sections, these three lines are concurrent, meaning they all pass through one common point, and that here is G. And that point is called the centroid, where your three medians intersect. Now, the most useful application of a centroid is that it's actually the center of gravity of your triangle there. If you were to cut this out of a piece of cardboard and try to balance it, you could balance it on a finger or the tip of a pen just by putting that pen at point G. It's kind of a neat little thing. Now, this theorem gets complicated, guys. It deals with the lengths of all of these pieces here. So what we're going to do is focus on this one median right here that goes from A to D with G as its centroid there. And G is not the midpoint of that median right there. That's important to understand. But what it does tell us here, guys, is that AG is located 2/3 of the way down the entire median. So there's three different ways you could say this, everybody. The measure of line segment AG makes up 2/3 of, means times, the entire median, which goes from A to D. That's one way to look at it. If this piece right here made up 2/3 of the median, that means that right here from G to D would make up 1/3 of the median. So another thing you could say is that the measure of line segment GD is equal to 1/3 of the entire median, which is AD. So that one would work. And the third thing we can write down is the relationship between AG and GD. Now, AG, we said, made up 2/3 of the median. GD only makes up 1/3 of the median right here. So what we would say in that case, a couple of ways to do it, is that line segment GD, this smaller piece down here on the bottom, is going to be half the measure of this larger piece, which is AG. So all three of those statements are true, and that can be difficult to keep track of. Furthermore, to make things even just a little bit more difficult, these last two can sometimes be rewritten in a different way that you might see from time to time. In this second equation, the one that's right here, if we were to multiply both sides of the equation by 3, you could also get the statement that 3 times GD would be equal to the measure of AD. That's just if I multiplied by 3. And in the statement on the bottom, that GD is equal to half of AG, if you multiply both sides of that equation by 2, you would get this statement. 2 times GD is equal to the measure of AG. So that's a lot, guys. There are 5 statements right there that are all true, and you kind of have to pick which one works the best, depending on the information that you have. So what I've got for you now is effectively the same example, or almost the same example, done 3 different ways and in 3 different settings, and we're going to walk through all of them. So our first one here says to solve for x if b is the centroid, okay? And they've given us the measure of AB, which I would say is the longer part of the median, and then they've given us AC, which is the entire median right there. So the question now is, what's the relationship between these two pieces? Well, if I'm looking at AB, the longer piece, and AC, the entire thing, then it kind of looks like, as I go back to this page, I'm talking about this statement right here, guys. The one that says that AG is equal to 2/3 of AD, and that's how we're going to set this one up. So in this case, here we go. The longer piece right here, AB, makes up 2/3 of the whole median there. So AB, which is 5x plus 1, actually, let me write that out first. AB is equal to 2/3 of the entire median, which was AC. So the measure of AB is 5x plus 1. Then that's going to equal 2/3 times the quantity of 6x plus 12. Now, we caught a break here, and I'll explain why later, but distributing isn't all that tough to do here, and we end up with some nice numbers. So 5x plus 1 is equal to 2/3 of 6. Guys, if you want to do this without a calculator, you're going to take the whole number, 6, divide it by the denominator, and then multiply it by the numerator. So 6 divided by 3 is 2, times 2 is going to get you a 4x right there. Plus, we do the same thing with the 12 now. 12 divided by 3 is 4, times 2 is 8. I'll bring the 4x to the left and just get an x. Subtract the 1 on the right and get x is equal to 7. A real quick check right here. 5 times 7 plus 1 would be 36, and 6 times 7, 42, plus 12 would be 54. And if you were to go to your calculator and ask it to simplify 36 over 54, it would divide an 18 out of both of those and give you 2/3, which is exactly what we thought we should get here. That larger piece, AB, is equal to 2/3 of the entire median. So that's one setup. In the second problem we have here, we've been given the measure of BC, which is the smaller piece down here on the bottom, and then AC, which again is the entire median. So in this case, I have to use the second of the 3 equations that we wrote down a couple slides ago. And we know now that BC, the smallest piece, is equal to 1/3 of the entire median, which is AC. So BC is 2y minus 3. That equals 1/3 times the quantity 4y plus 9. Now on this problem, I was a little bit mean to you guys intentionally because I wanted to show you something different. We could absolutely distribute the 1/3 here if we wanted, but 1/3 times 4 is not going to work out well, and it would get you 4/3 y. We could handle it, and the calculator wouldn't mind. But there's another idea that I'd rather talk about. If you wanted to get rid of that 1/3, another thing you could do is multiply both sides of this equation by 3. So you'll notice I'm using some brackets right here, and I'm doing the exact same thing on both sides. And the reason we do that is so that this 3 and this 1/3, which are reciprocals of one another, will cancel out. I'm going to distribute the 3 on the left and get a 6y minus 9 equals and then just a 4y plus 9 on the right. So just multiplying both sides by 3 enabled us to get rid of all of the fractions, and now we have this nicer equation. We're going to end up with a 2y on the left and get an 18 on the right, and y equals 9 is going to be our solution. Quick check here, guys. 2 times 9 is 18, minus 3 is going to be 15 for the measure of BC. And then AC, 4 times 9 is going to be 36, plus 9 will get us 45 for the entire median. And one more time, if we tested this, 15 over 45 simplifies to 1/3, which is what we wanted. BC, this small piece, only makes up 1/3 of the median. And the third and final example I have for you is a little bit different. This one deals with AB, which is the longer part of the median, and then it deals with BC, which is the smaller part. So in this case right here, guys, 2 ways of doing this one, but our setup right here, if I go back to the 3 equations that we wrote down here, we would be looking right now at this third one here, guys. The lower piece, GD, was half of the upper piece, which was GD. So in this case, again, trying to do that consistently right here, our lower piece, BC, would make up half of the larger piece, which is AB. So a 2z plus 9 is going to be equal to 1/2 of the quantity 7z plus 3. Now again, with 2 odd numbers here, distributing a 1/2 in there is not going to end up real pretty. So what I'm going to do instead is multiply both sides of the equation by the reciprocal of 1/2, which is just 2. We're going to distribute the 2 here, and the 2 and the 1/2 on the right are going to cancel. We get 4z plus 18 is going to equal a 7z plus 3. Okay, I'm going to bring my 4z over to the right, and 7z minus 4z is 3z. We'll subtract the 3 and get a 15 over there on the left, and divide by 3, and we'll get a z is equal to 5. Let's double check that real quick. That is 35 plus 3, 38 for the measure of AB right there. And then BC looks like it's going to be 19. So we've got that. 38 is double 19, so that's good. The measure of AC now would end up being 38 plus 19, which would be 57, and I think everything there works out the way that we want it to. So feel good about that answer right there. So medians are a lot, guys, so that's quite a bit to ingest off that section. Now, the author decided to throw the 4th segment here as well and combine this instead of giving it its own section, which sounds tough, but altitudes are actually the easiest of the 4 things to work with, guys, and not very much happens. They don't have a whole lot of practical consequence. So an altitude, and you've probably heard that word when we're talking about the height of an airplane, an altitude is a segment that goes from a vertex of a triangle that is perpendicular to the opposite side of that triangle. So that's what I want to underline right there, perpendicular to the opposite side. So 3 different ways that an altitude can present itself. I've got 3 triangles here, and you'll notice that the first one I have drawn is acute. The second one that I have drawn here looks like a right triangle, and the third one is an obtuse triangle. In each one of them, we're going to draw the altitude that goes from point A to line segment BC. So the altitude in the first triangle starts at point A, and it needs to go perpendicular to the opposite side. So in this case, our altitude from A to BC is going to drop straight down here, forming a right angle. And that's what the altitude in the first triangle looks like. What we just drew is the only line segment that comes from point A perpendicular to BC. Now in the second triangle, we try to do the same thing. We start up top here at point A, and now we're going to try to draw the only segment we can perpendicular to BC. Well, the interesting thing here is that segment that we're drawing right here is one of the original sides of the triangle. So in a right triangle, if you're starting from an acute angle, your altitude just ends up being one of the legs of that right triangle. And the really interesting thing is what happens when you try to do this in an obtuse triangle. If we start at A and want to draw an altitude that's perpendicular to BC, well, guys, it's not going to be that. That's not a right angle. It's not going to be that. It's not going to be that. If you wanted to actually draw a right angle from A to BC, you'd kind of have to cheat, and you'd have to extend BC a little bit past where it ends right now, and the altitude is actually going to go outside of the triangle looking like that. So 3 different cases here, guys. In an acute triangle, your altitude is located inside your triangle. In a right triangle, your altitude is located on the triangle. And in an obtuse triangle, your altitude is located outside of the triangle. 3 different things can happen in a case like that. So not a whole lot to do with altitudes. Here's one problem right here. This point is a little bit out of place. Sorry about that. It says that line segment BD is an altitude of triangle ABC, and we're supposed to solve for x. Well, the fact that they've told us that we have an altitude tells us that this right here has to be a right angle. And they've told us that the measure of angle CDB is 7x plus 6 degrees. Well, because it's an altitude, we know this is a 90-degree angle, so there's our equation. 7x plus 6 has to be equal to 90 degrees. Subtract the 6, we're going to get 7x equals 84. Divide by 7, and we're going to get x is equal to 12. So some of these altitude problems can be really straightforward. And the last slide I have for you guys is this theorem right here called concurrency of altitudes. And this one simply says that the 3 altitudes of any triangle are going to intersect at a point called the orthocenter of the triangle. So in this diagram right here, because of the 3 right angles that we have, we can tell that each of these segments is an altitude. The segment I just highlighted came from point B and went perpendicular to the opposite side. The same thing happened here from A, perpendicular to line segment BC, and from C, perpendicular to line segment AB. So those 3 altitudes all intersect here, and that point right there is called the orthocenter. So I'll just call that a point O right there, and the orthocenter is that point there. Now you'll notice it doesn't say anything about the usefulness of an orthocenter. That is because relative to the other 3 special points that we've talked about, an orthocenter really doesn't do anything cool. It's simply the point where those 3 altitudes intersect. But as far as I'm aware, there's not really a nice application of that the way there was with a circumcenter or with an incenter or with a centroid. All right, everybody. Thanks for following through here and listening to my scratchy voice. That's a wrap on section 6.3. Good luck on that homework.